Design and fabrication of microfluidic devices using soft lithography. This process consists of two main parts. First one is soft photolithography to prepare the mold, and the second one is to use this master for making PDMS channels. Firstly, we will ensure that we have a hydrophilic substrate surface. It is better to have a silicone wafer as a substrate, but due to expensiveness of silicone wafer, you can also use a glass slide as a substrate. Here in Pias, we do have bunch of silicone wafers available, but our supervisor advises us to use the glass slide as a substrate as a precautionary measure, so that we can be used to with the process of lithography and use the silicone wafer when we will be expert at this process. So that's why we are using glass slide here. To make substrate surface hydrophilic, we use argon plasma treatment, which raises the surface energy of the substrate. This is essential to promote the adhesion between glass slide and SU8 photoresist. Treat your glass slide substrate in plasma machine for sufficient amount of time to improve the hydrophilicity. We found that the treatment time of 10 minutes around 3 torr gave good results. The hydrophilicity of silicone wafer is defined by the contact angle of a water droplet. You can do a simple visual test by placing a water droplet on the surface of the wafer. If the droplet is flat, surface is hydrophilic. Here you can see the difference between the treated and untreated surface. Notice that dome shape on the untreated surface. Plus, the plasma treatment also helps in cleaning off the substrate at micro level. The next step is to spin coat the substrate with the photoresist. We use SUA2075 photoresist for our experiment. For achieving thickness of 200 microns, we spin the spin coater at 1300 rpm. But wait a minute, how we find out this value? Don't worry, we will tell you. Download the datasheet of your photoresist and extract values from the graphs provided by the manufacturer. Step 3 is to soft bake the substrate. Soft baking is required to evaporate solvent from the photoresist. This improves the adhesion between photoresist and the substrate. This allows UV maskant to be applied without sticking. You can refer to photoresist datasheet to get recommended time and temperatures for your product. We found 7 minutes at 65 degrees followed by 35 minutes at 95 degrees from the datasheet. Then allow the substrate to cool to room temperature before moving to the next step. Step 4 is the UV exposure to cure the photoresist. You should have UV photomask with your design printed on them like this one. Several guides are available online to help you create your design at any CAD software like SolidWorks. If you want to make your design from us, you can contact at the numbers given below in the description. Place your photomask onto the photoresist. The recommended exposure dosage of the UV can be found from the datasheet. We have found 45-second exposure time suitable according to our 200 micron thickness requirement. Step 5 is the post-exposure baking. This evaporates more solvent, improves the adhesion of the photoresist and the substrate. It also reduces the stresses by promoting mechanical relaxation. Refer to photoresist datasheet for timing guideline. In our case, we find that 5 minutes at 65 degrees and 15 minutes for 95 degrees, and then cool down for the next step of developing. Now here is the key to check that your design was sufficient exposed to UV or not. If your pattern becomes visible after post-exposure baking, then it implies that UV exposure was sufficient, or vice versa. Then we can move on the developing the channel. We use SUA developer for developing the channel. In our case, we found that the development time of 15 minutes is enough for us. Submerge the baked substrate into the SUA developer and then also clean it with SUA developer too. For drying it, you can use air compressor to achieve better finishing. Part 2. Now we can move on to the second phase of the process, that is PDMS casting. Mix the PDMS elastomer and the curing agent in 10:1. First put the beaker on weight balance, set it to 0, then add some elastomer in the beaker. We add almost 52 grams PDMS elastomer, so in 10:1 we add almost 5 grams of curing agent. Rigorously mix them to form solution. This mixture contains a lot of bubbles and we have to remove them. Therefore, we place the solution in the vacuum desiccator for degassing. But it was taking a lot of time. So, we found out a hack from our personal experience and thinking. We have a plasma chamber in which we created vacuum in the start of the video. So, we thought, why not to use that vacuum chamber as a degasser? Because simple physics is that bubbles will rise due to pressure difference. In vacuum desiccator, we cannot achieve very low pressure, but with vacuum pump, we can significantly reduce the pressure, which helps to remove the bubbles rapidly. Here you can see in the chamber that how bubbles are rising up and bursting on the surface. It will make your solution crystal clear and ready for the casting. PDMS casting is very easy. Just pour the PDMS solution over the prepared mold and then place it in oven for curing at 3 to 4 hours at 65 degrees centigrade. After baking and cooling it down, take it out of the oven and peel off the PDMS. Your device is almost ready, just you have to insert the holes by punching hole in it, and you have to plasma bond the PDMS with another glass slide or PDMS, whatever you want. In our case, we use PDMS bonding with PDMS. Make sure to do plasma treatment around 1 to 1.5 minutes depending upon your plasma gas. Make sure the channel side is up in the plasma chamber, and after doing plasma treatment, take out both from plasma chamber and firmly press both together for bonding. Please be in hurry because plasma treatment effects not last for so long. This bond is very weak at this time, but leaving the device at 60 degrees centigrade for 3 days make this bond very strong. After glass slide, we repeat the same process on silicone wafer, and you can see the results here.
Hello guys, my name is Muhammad Abdullah Syal.
And my name is Muhammad Mannan Nasir, student of BS Mechanical 2024 in Pyas.
I hope you like the video. Our final year project is on design and fabrication of microfluidic device using soft lithography.
We have put our all efforts and experience in this video, so make sure to like the video and subscribe the channel and share this video with the ones who are interested in microfluidics. And most important, if you find anything doubtful, let me know in the comment section and we shall try to reply as soon as possible.